So today we're diving into a highly technical developer journal entry. It's from August 22, 2026.
Right.
And it's really just a few lines of Haskell code, posted by a developer who goes by the name Ang. But buried in this little snippet is this massive masterclass on cognitive load, software architecture, and I guess why the most important work in any complex system usually happens, long after the initial build is considered done.
Yeah, it really challenges that whole idea that software is ever actually a finished product.
Yeah.
I mean, we were looking at a post titled Notes on Haskell Programming Part 220.
Part 220.
Right, Part 220. And the focus of this specific entry, it isn't like a massive feature launch or a big overhaul. It's a hyper-focused refactoring of how errors are handled in the code.
Yeah, just the stamina required to maintain a journal of that length, 220 parts just about programming notes is honestly impressive. But okay, let's unpack this because to understand what Ang is actually doing here, we really have to look at the environment that they're working in. So the post starts by noting that they've just finished a migration from a, quote, regular to custom IO monad. And I feel like for those of us who follow software architecture, but maybe don't write Haskell every single day, that phrase definitely needs a bit of translation.
It definitely does, yeah.
Yeah.
So Haskell is a purely functional programming language. And what that means is, well, in a lot of languages like, say, Python or JavaScript, you can just write a function that calculates a math problem, and right in the middle of it, you can just tell the system to, I don't know, print a message to the screen or read a file from the hard drive.
Right. You just inject a print statement wherever you want, like print hello world right in the middle of a loop.
Exactly. But Haskell doesn't allow that. It enforces this strict purity. So a function that calculates a value can only calculate a value. It can't have these things called side effects, like talking to the outside world.
Because the outside world is messy.
Yeah, it's messy, it's unpredictable, files might not exist, or the network goes down. So to handle that messy reality, Haskell uses something called an IO monad.
Okay.
And you can sort of think of it as a tightly controlled hazardous materials suit.
A hazmat suit.
A hazmat suit, yeah.
Yeah.
Any operation that interacts with the unpredictable outside world, it has to be wrapped in this IO monad so it doesn't infect the pure predictable logic of the rest of the program.
Okay, I like that. So the standard IO monad is Haskell's built-in hazmat suit for dealing with side effects.
Right.
But Ang mentions migrating from a regular IO monad to a custom one. So why would you need a custom version of something that's already built into the language? I'm trying to think of an analogy. Is it like upgrading from, say, a generic multi-tool like a Swiss Army knife to a highly specialized custom-built toolkit that's designed perfectly for your specific job?
That's a perfect analogy, yeah. Because the standard IO monad is generic. It just says, hey, this action talks to the outside world. It doesn't know anything about the specific business logic of your application.
It's just a generic hazmat suit.
Right. One size fits all. But we connect this to the bigger picture. Like, as an application grows, you often need to track specific configurations or maybe manage specific types of domain errors across your entire program. And instead of passing those configurations down manually through every single function, which is tedious, developers build a custom environment.
Okay.
And this is often called an app monad. It wraps those standard I/O capabilities, but it adds layers of specialized context that only their specific application cares about.
Okay, wait. So if this custom app monad is so specialized and so efficient, why are we looking at a journal entry where Ang is still, kind of complaining about having to clean things up? It sounds like maybe they made a mistake during the migration and left a bunch of, I don't know, scaffolding behind. Like if you move into a new house, the furniture is in, but you still have a bunch of weirdly placed boxes in the hallway.
Yeah, exactly. The boxes in the hallway. That's exactly where Ang is right now. And it's a fair assumption to look at that and think, oh, it's a mistake, it's technical debt. But actually, large-scale migrations in functional programming, they're almost always done in phases.
Specifically to prevent the whole thing from crashing down.
Yes. When you swap out the fundamental foundation of how a program talks to the outside world, your first goal is literally just making sure the program compiles and runs.
Right.
You brute force the compatibility. You don't optimize for elegance on day one.
You just get it working.
All right. You get it working. And that brings us to the core problem that Ang is addressing in Part 220. The heavy lifting of the migration, it's over.
The new house is built.
The house is built. The custom app monad is in place. But the code base is now littered with The brute force plumbing they use to make the old error handling system talk to the new custom environment.
And Ang actually identifies the exact piece of plumbing that's causing the problem.
Yeah.
It's a specific string of boilerplate code, and I'm just going to read it here. It's lift.io, then a less than sign, and a pipe, so that's the apply operator, and then throw.io.
Yeah.
So lift.io pipe, throw.io. According to the journal, this is scattered all over the codebase. Whenever the program encounters a problem, it basically has to recite this exact phrase before it can actually specify what the error is, which is kind of like, it's like having to recite your full legal name, your date of birth, and your social security number every single time you want to order a coffee.
Right.
Instead of just handing the barista a loyalty card, it's just exhausting repetition.
It is, yeah. And let's look at the errors Eng specifically lists in the post, because it shows how often this happens. The program is constantly running checks. So it needs to know if a file is missing, which triggers file not found.
Okay.
It checks if a read operation failed, triggering read failed.
Right.
It checks if a file is the wrong format, throwing not text file. Or if the text encoding is wrong, resulting in invalid show 8.
So just based on those specific errors, it sounds like this program is, I don't know, some sort of data processing pipeline or a command line tool that aggressively parses local files.
Yeah.
Because it has to be highly defensive about what it's reading.
Almost certainly, yeah. And in a statically typed language like Haskell, being defensive means being explicit. You can't just let the program crash silently. You have to declare every single failure state. But the friction here, it arises because of how these errors are being thrown in the new custom environment. Because Eng moved to this custom app monad, they can't just use the standard throw.io function by itself anymore.
Okay, wait, why not? If throw.io throws an IO exception, and they are still fundamentally dealing with IO stuff, like missing files, shouldn't it just work?
Well, because the types don't match anymore.
Oh, right.
Yeah, throw.io operates in the standard IO environment, but Eng's program is now living inside the custom app environment. If you try to hand a standard IO error to the custom app monad, the compiler just rejects it. They don't speak the exact same language anymore.
Ah, okay, so that's where the lift.io part comes in. It's functioning as a kind of translator.
Exactly. Yeah, lift.io is an adapter. It takes an operation from a lower, simpler context, standard IO, and it literally lifts it up into the more complex layered context of the custom app monad so it can actually be executed there. So to throw a simple file error, Eng has to tell the system, okay, take this domain error, turn it into a standard IO exception using throw.io, and then lift that exception into the custom app environment using lift.io.
Wow. Which results in writing, lift.io, throw.io, file not found every single time.
Yeah.
And I see the mechanics of it, but let me challenge this just a little bit.
Sure.
Because a lot of developers working in languages like, say, Java or Go, they're incredibly used to writing boilerplate. I mean, in Go, you type if error not equal nil hundreds of times a day.
Yeah.
It's just muscle memory. So why is Eng dedicating an entire journal entry to stripping out 2 tiny function calls? Is it really that big of a deal?
It is a massive deal when you consider how working memory functions during programming. Because boilerplate isn't just a typing annoyance, it's visual noise, and it degrades code readability. When a developer looks at a block of code, they're trying to parse the business logic, the intent of the program.
Right. You want to read what the code is doing, not the mechanics of how the language forces it to compile.
Precisely. If your eyes have to stumble over lift.io and throw.io 50 times in a single file just to see that, oh, a file wasn't found, you are burning cognitive bandwidth on plumbing instead of architecture.
Wow.
And in functional programming, where functions are often really highly compressed and mathematically dense, that signal-to-noise ratio is everything.
Okay, that makes sense. The plumbing is distracting from the actual flow of water.
Exactly.
So let's look at how Eng actually fixes this, because they decide to centralize this translation process into a single helper function, which they name throw_app. And the journal gives us the exact implementation, and it is remarkably brief.
Yeah, it's literally just 3 lines. The first line is just a comment set in the intention. It says, throw a domain apper through the app monad as an IO exception.
Right.
Then the second line is the type signature, defining the contract for the compiler. It's throw_app, : epper app A.
Okay.
And then the third line is the actual execution. Throw_app equals lift.io.throw.io.
See, what's fascinating here is how functional programming handles abstraction. That third line throw_app equals lift.io.throw.io. It doesn't even mention the specific error being passed in. It just uses a dot to compose the 2 functions together.
Yes. That is a pattern called point freestyle.
Point freestyle.
Yeah. It mathematically composes lift.io and throw I/O into a brand new single-function pipeline. The data will flow through throw I/O and then immediately pipe into lift I/O. By defining this just once, globally, Ang creates a single funnel.
And here's where it gets really interesting, I think, because this highlights the fundamental leverage of software refactoring. You define a rule in one place, and you instantly have the power to alter the fabric of a massive code base. Aang essentially built a custom adapter plug that lives in the wall, so now the rest of the application doesn't have to carry around all the messy wiring.
And that abstraction pays immediate dividends in the actual text of the code. Aang provides a diff in the journal entry, a comparison of the code before and after this refactor.
Yeah, let's walk through these diffs, because looking at them side by side, it really demonstrates your point about the signal-to-noise ratio. It's one thing to talk about cognitive load abstractly, but you can practically hear the difference when you read the changes. Let's volley these back and forth. You read the legacy code with the brute force plumbing, and I'll read the refactored version.
Sounds good. We'll start with the file existence check. Before it was, unless exists, apply lift IO, apply throw IO, apply file not found path.
God, that's a mouthful. Okay, and after, it's just unless exists, apply throw app, apply file not found path.
So much cleaner.
Okay.
Next, handling a read failure. Before.c, left arrow, either const apply lift IO, apply throw IO, apply read failed path, pure content.
And after text C, apply throw app, apply read failed path, pure content.
Validating the file type. Before, unless it's text C, apply lift IO, apply throw IO, apply not text file path.
After, unless is text C apply, throw app apply not text file path.
And finally, checking for invalid formatting. Before. Unless is OSHI F8C apply, lift IO, apply throw IO, invalid down him.
And after, unless is use F8C apply, throw app, invalid UT F8. Just reading that.
The rhythm of the refactored code is so much cleaner.
Yeah.
Like throw app invalid UTF8 basically reads like plain English. Throw application error invalid UTF8.
Exactly. The mechanical adapter, the fact that this is an I/O exception being lifted into a custom monad, it's completely hidden from the developer reading the business logic.
It's just out of the way.
The intent is laid completely bare.
And there is a specific piece of context surrounding these diffs that Aang included, which I think really drives this home. At the very end of the final snippet, Aang shows the environment where this error handling is taking place. And the line is, when tidy flag and FMT does not equal TSD.
Right, that conditional statement.
Yeah, and even without knowing the entire architecture of Aang's program, we can deduce what's happening. The program is running a complex Boolean check. It's evaluating if a tidy flag has been triggered by the user, and simultaneously checking if the format of the current document is not a text file. So it is juggling multiple state conditions right there. And that is exactly when cognitive load matters the most. Error handling, it rarely happens in isolation. It is usually deeply nested inside intricate logic branches.
Right.
If you are a developer, your brain is currently holding the state of tidy flag and the state of FMT in your working memory, trying to figure out what the program is supposed to do next.
And if you suddenly hit lift IO, throw IO right in the middle of trying to resolve that logic, it just breaks your concentration. It forces you to drop the business logic for a split second to parse the monad plumbing.
Exactly. By replacing that plumbing with throw app, Aang ensures that the error path is frictionless. You see the error condition, you understand it instantly, and you maintain your grasp on the overarching logic of the tidy flag and the formatting rules. It's defensive programming that actually respects the human who has to read it.
Okay, so what does this all mean? We've spent this time digging into monad transformers, function composition, point-free style, and Haskell. But the reason we pulled this specific entry from August 2026 isn't just to talk about functional programming syntax. It's about the broader philosophy of maintaining complex systems, right?
Yeah, absolutely. It is about the discipline of continuous improvement. Aang could have easily left the lift IO, throw IO code in place.
Yeah, it worked.
The migration was successful, the code compiled, the application functioned exactly as intended.
User wouldn't know.
The end user of the software would never, ever know the difference.
But the developer would, and the team maintaining it would. The friction would compound over time. Every new feature would require writing more boilerplate. Every bug hunt would require reading through more visual noise.
This raises an important question, though, like, how often do we declare a project done just because it fundamentally works, while completely ignoring the internal friction we've generated in the process? Aang signs off the journal entry by noting, quote, "Of course, there are still numerous tiny changes we can further refactor, but that would be another future discussion."
I really appreciate that pragmatism. It acknowledges that there is no magical finish line where the code base is pristine and flawless. Technical debt is just a natural byproduct of forward momentum. When you migrate a system, you leave debris behind.
Right, the boxes in the hallway.
Yes, the boxes in the hallway.
And managing that debris isn't a failure of the initial design. It's just the reality of engineering. Real engineering is looking at a working system, identifying the repetitive manual translations you're forcing your brain to do, and building an abstraction, your own personal throw app to handle it quietly in the background.
That's a powerful framework. Whether you are managing a monolithic code base or organizing a massive database or even just structuring the workflows of a large team, right? There are always brute force adapters that were put in place just to survive a transition. Finding those and smoothing them out is the actual work of maintenance.
But there is a flip side to this that I think we really have to consider, especially given the landscape of software development right now.
Oh, really?
Yeah, we are looking at this meticulous, handcrafted refactoring process by Ang. But if we pull back and look at the rise of AI coding assistance tools that can generate thousands of lines of code in seconds, the dynamic fundamentally changes.
Oh, wow. That's an interesting pivot because an AI doesn't experience cognitive load.
Exactly. If an AI coding assistant is writing this Haskell code, it has zero problem typing out lift IO, throw IO 500 times across 50 different files in a fraction of a second.
Right. It doesn't get tired.
It doesn't get annoyed by the repetition. It doesn't lose its train of thought when parsing a complex tidy flag condition.
So the AI would never feel the friction that prompted Ang to create throw app in the first place.
Precisely. And that begs a really provocative question, I think. If AI assistants eliminate the physical pain of writing boilerplate, and they can flawlessly parse the visual noise that exhausts human developers, do we eventually lose the muscle memory of refactoring?
Wow. If the machine writes the messy plumbing for us and reads the messy plumbing for us, we might just stop building elegant abstractions entirely.
We could end up with sprawling, hyper-complex code bases that compile perfectly and run flawlessly, but are so dense with unrefactored boilerplate that no human being could ever step in and understand the core architecture without an AI translating it for them.
It's like a black box.
The code base becomes a black box of infinite plumbing.
That completely flips the lesson of Ang's journal entry on its head. Ang's refactoring wasn't just about making the code prettier. It was an act of preserving human readability. It was about making sure the intent of the system remained comprehensible to the human mind. If we outsource the tolerance for boilerplate to an algorithm, we might be sacrificing our own ability to understand the systems we are building.
It makes you wonder if the quiet, continuous act of refactoring isn't just about efficiency. Maybe it's the critical mechanism that keeps a developer anchored to the reality of their own software. The friction forces you to understand the system deeply enough to simplify it.
That is a phenomenal thought to leave on. The friction is the anchor. As our tools get faster and our systems get more complex, maybe the most radical thing we can do is slow down, look at the plumbing we've just built, and ask ourselves how to make it human again. Keep looking for your own throw up, everyone. We'll catch you on the next deep dive.